We use it every single day. We flip a switch and the lights come on. But have you ever really stopped to think about how electricity actually works? Well, it turns out the answer is way more surprising, and honestly, way cooler than what most of us learned in school. Okay, let's get right into it.
So, let's just start with the biggest question of all. What is electricity? I mean, really, if you had to explain it to someone right now, what would you even say? It's tougher than you think.
And here's the first little twist. You can't actually see electricity itself. It's invisible. What we see are its effects, right? We see the light from a bulb, we feel the heat from a toaster, we see the motion from a fan's motor, or sense the magnetic fields they all create. We're only ever seeing the work it does, not the thing doing the work.
Now, to really get what's going on, we have to travel back in time a bit and correct a huge misconception. I'm talking about a mistake that's over 250 years old, and in a lot of ways, we've had the whole thing literally backwards ever since. Okay, so picture this. It's the 1700s. Benjamin Franklin, brilliant guy, comes up with a theory. He guesses that electricity is some kind of invisible fluid that flows from a positive point to a negative one. And for the time, that was an amazing guess. But that's all it was, a guess. It wasn't until 1897 that a scientist named J.J. Thomson actually discovered the electron, a tiny negative particle, and proved the flow was actually the other way around.
And this really shows you the difference. Franklin's guess is now called conventional current. And get this, you'll still see it in tons of circuit diagrams today, showing a flow from positive to negative. But the reality, what's physically happening, is called electron flow. The actual particles doing the moving, the electrons, are flowing from the negative terminal towards the positive one.
All right, before we get to the really mind-blowing part of all this, let's build up our intuition with a classic analogy that I'm sure you've heard before. Just imagine for a minute that an electrical circuit is like a big system of water pipes. Yeah, the ideas map out pretty well, you know? Voltage is just like the water pressure you get from a pump. It's the electrical push. Current, measured in amps, is the flow rate, like how many gallons of water are moving past a point per minute. And resistance, well, that's like a narrow, pinched section of the pipe that makes it harder for the water to get through. It's a really good starting point, but as you're about to see, this is where the simplicity ends. So, let's ditch the analogy and zoom way in. I mean, all the way down to the atomic level to see what's actually happening inside that copper wire. So a copper wire is just made of trillions and trillions of copper atoms. And each one of those atoms has an electron in its outermost shell that's, well, not really attached very tightly. We call this a free electron, and it's the star of our show. It can easily jump from one atom to the next. Okay, this part is absolutely crucial. That wire isn't an empty pipe waiting for electrons to flow in. No, it is already jam-packed full of these free electrons. Before you even connect a battery, they're in there, buzzing around like crazy in every possible direction. Totally random, like a chaotic crowd of people in a hallway. And this brings us to the real heart of the mystery of how electricity works. And I gotta tell you, you might want to brace yourself for this next part. So let me ask you, you flip a light switch. How fast do you think the electrons from that battery or power source have to race down the wire to get to the light bulb and turn it on? Gotta be fast, right? Like nearly the speed of light? The real answer is, wait for it, slower than a snail. No, I'm not kidding. The actual drift speed of a single electron in a normal circuit is less than 1/10 of a millimeter per second. It would take hours for one electron to travel just a few feet down a wire. So what gives? This is the big paradox, right? If the electrons themselves are moving at this ridiculously slow crawl, why does the light turn on the very instant you flip that switch? How is that possible? The answer is so simple and so profound. It's because it's not the electrons that travel fast, it's the energy. So what is really happening in that split second when you complete a circuit? This is where the story gets really, really cool. Okay, here's the play-by-play. The moment you connect a battery, it creates an imbalance. This causes an invisible gradient of charge to build up on the surface of the wire itself. Now, this surface charge projects a powerful electric field throughout the entire inside of the wire. And it's this field, this wave of energy, that expands down the wire at almost the speed of light. It's like a command that shouts down the line, telling all the free electrons that are already there to start drifting in the same direction. So you see, the electrons that actually make your light bulb's filament glow were already right there in the filament. waiting. They just needed the signal from that super fast electric field to get moving. The energy is delivered by the invisible field, not by one specific electron making a long trip from the battery. As the source material puts it just perfectly, it's the electric field in the wire that accelerates them to deliver the energy where needed. A great way to think about it is like a pipe that's already full of water. When you turn on the tap, the pressure wave moves instantly, and water comes out the other end right away. You're not waiting for a drop of water to travel the whole length of the pipe. So it's this invisible, lightning-fast field that's truly powering our entire modern world. It's not a flow of particles, but a wave of energy. And it really makes you wonder, doesn't it? What other incredible, invisible forces like this are shaping our reality in every single moment?